Welcome back to Machine Learning for Mathematicians. This is Lecture 3, and it is the translation lecture. We derived nothing new today. Instead, we learned to read a paper and its code side by side. The reading is section 3.2.1 of Vaswani and co-authors. Attention is all you need. Read it beside a minimal implementation. Alongside that, prints Appendix A, notation. Let me say openly why a lecture with no derivation in it is worth 20 minutes. The thing that stops a capable mathematician reading a machine learning paper is almost never the mathematics. It is that the mathematics arrives wearing other names and nobody prints the dictionary. So the gap is lexical, not mathematical. It comes in exactly three kinds. First, a symbol became an identifier. Eta became LR, epsilon became epsilon, and theta became whatever the parameters method hands back. Second, an index became an axis. A summed index is a contracted axis, and a free index survives into the output shape. Third, a constant went somewhere the paper does not mention. So here is the job of this lecture. By the end, you should be able to open a paper and a repository side by side. Then, for every symbol you can say which identifier it became, or that it became none. One standing hazard first. The notation is not standardized, and nobody is coming to fix it. Analysis had 3 centuries to agree on what the integral sign means. This field has had about 15 years and has agreed on almost nothing. The same letter means different things. Alpha is a step size in one paper, a mixing weight in the next, and a tension weight in the one after. Sigma is a standard deviation, a nonlinearity, and a logistic function. The same quantity also gets different letters. A step size is eta, alpha, gamma, or epsilon, and shapes are given in prose or not at all. 2 papers can both write QK transpose and mean transposes of one another. So translation is a skill, not a lookup table. When the notation is ambiguous, the only reliable move is to make the library tell you by running it. The verification frame in part 3 does exactly that, on a constant that no interface exposes. First, the Greek letters. Which identifier did each one become, and which of them survive in the code at all? The pattern here matters more than any single row. Every Greek letter lands in one of 3 statuses. It is an argument you may change, an attribute you may only read, or it has no counterpart in the code at all. Take theta. In the mathematics, theta is one vector in a space of some dimension. In the code, there is no such object. You get an iterator over many tensors of many shapes, and the flat theta is never formed. Take sigma. In a formula, sigma is a standard deviation. In the code, the identifier called running variance holds a variance, so the square root lives in the arithmetic and never in the name. Eta becomes LR, an argument on the optimizer, and a scheduler overwrites it during training. Lambda becomes weight decay, which sits on the optimizer and not in the loss you wrote. And epsilon becomes epsilon twice over, meaning 2 different things. Names are the second layer of the problem, and these 5 sit on the first page of every implementation you will read. A linear layer computes wx plus b, which is affine and not linear. It is linear only when the bias is switched off and the default is on. The weight of that layer has shape out by in. So the w of the mathematics is stored exactly as the paper writes it, then applied with a transpose. Lecture 2 showed that transpose costs nothing. Logits are unnormalized log probabilities, fixed only up to an additive constant. They are genuine log odds, only in the 2-class case. Calling backward on the loss returns nothing at all. It populates the grad attribute on the leaves, accumulating into whatever is already there. The gradient is a side effect, which is why forgetting to zero it bites. And criterion is a loss function, not a rule for choosing an action. Here is the cleanest case of a name that does not determine a meaning. 2 constants, both called epsilon, both small and positive, both added for stability. In layer normalization, we subtract the mean and divide by the square root of sigma squared plus epsilon, so epsilon sits inside the root. In atom, we step by m hat over the square root of v hat plus epsilon, so epsilon sits outside. No paper tells you which is which, so we ask the library. Each row is one hypothesis. Epsilon inside the root reproduces layer normalization to about 4 in 10 to the 16th, which is machine rounding error. Epsilon outside is wrong by about 9 in 10,000. For atom, the pattern reverses. Outside agrees to 0. Inside is wrong by about 4 in 10,000. So, a shared name is not a shared meaning. Lecture 11 derives the layer normalization placement, and Lecture 16 the atom one. Today, the point is only this. A run settles the question in 4 lines, and reading does not. Next, indices. What happens to a summed index when a formula becomes an array expression, and where did the batch go? The paper writes one example at a time. Y sub I equals the sum over j of w sub I, j times x sub j, plus b sub I. 2 indices, 2 different jobs. The index j occurs twice and is summed, so j is contracted. It disappears. The index I occurs once on each side, so I is free. It survives into the output shape. Now restore the sample index k that the paper suppresses, and the code writes itself. Y sub ki equals the sum over j of w sub I j times x sub kj plus b sub I. In code that is in sum of the string ij, comma, kj arrow ki applied to w and x plus b. So read an in sum string as mathematics. It is index notation with the summation signs deleted. Compare the 2 sides of the arrow. A letter absent from the output is summed over, and a letter on both sides is free. Papers state everything per example, because that is where the modeling assumptions live. Code states everything per batch, because that is where the throughput lives. Nothing in between is written down, and the reader is expected to insert it. So the leading axis is a silent index. It is never summed over, never named in the equation, never contracted with anything. Every broadcasting rule in the library exists to keep it silent. Let us check it. Write the affine map twice, once as a loop over the sample index and once as the batched expression, and compare. The 2 agree to about 7 in 10 to the 15th. That is not 0, and the reason matters. The 2 computations sum the same products in a different order, and floating point addition is not associative. So they are entitled to differ in the last bits of the mantissa. Lecture 10 is about when a difference like that stops being rounding and starts being the answer. A paper writes the loss as a sum over examples or as an expectation. It treats the difference as cosmetic because the minimizer is the same. In code, that difference is a keyword argument with the default, and it is not cosmetic at all. With the mean reduction, the loss comes out at about 2.58. With the sum, it comes out at about 165. The ratio is exactly 64, which is the batch size. The gradients behave the same way. The gradient norm is about 1/10 under the mean and about 7.9 under the sum. The ratio is again exactly 64. Here's what to carry away. Take a paper that writes a sum and run it with the library default. It differs from the paper by a factor of the batch size in the effective learning rate. Lecture 1 fixed the mean convention for this course precisely so that this never happens twice. Not every reduction is an average over samples. Most are contractions over a feature axis, and there the question is, what happened to the axis? A reduction deletes the axis it reduced. Ask for keep dim, and the axis stays with length 1. Length 1 is exactly what broadcasting needs in order to stretch it back. So x sub I minus x bar, written in one symbol in the paper, only aligns if you ask for the axis to be kept. The failure is not an exception. Shapes are aligned starting from the last axis and working forwards. The subtraction either raises an error or, when 2 lengths coincide, silently returns garbage of the correct shape. So, the thing to remember: a trailing axis of length 1 is the most common silent bug in the field because it is the only shape error broadcasting will forgive. Lecture 2 gave the alignment rule, and the discipline is to print the shape whenever a reduction and a subtraction meet. Third, the constants, a 1/2, a square root, and epsilon. Where does each of them actually live in the code? Constants that became defaults, and again the pattern matters more than the rows. Ask 3 questions of each constant. Where does it live? May you change it? And who justified the value? The 1 over the square root of d sub k in attention answers the second question with no. It is a default inside the kernel and an attribute of no module. It is not exposed at all. which is why we are about to recover it by measurement. Lecture 22 derives it. The epsilon in layer normalization is an argument defaulting to 10 to the minus 5, and it sits inside the square root. That is lecture 11. The epsilon in atom defaults to 10 to the minus 8 and sits outside. That is lecture 16. The two atom decay rates arrive as one tuple, defaulting to 0.9 and 0.999. The bias correction they force is lecture 16. And weight decay defaults to 0 on almost every optimizer, but not on atom W, where it defaults to 100th and decays whether you ask for it or not. Every textbook writes squared error with a 1/2 in front. The half is there, so the 2 from the power cancels and the derivative comes out clean. The library does not do that, so measure the gradient norm both ways. The half version gives about 0.27. The plain version gives about 0.54. The ratio is exactly 2, and the library's mean squared error carries no 1/2. The half is a convenience of exposition, and the library declined it. The minimizer is untouched, because scaling an objective by a positive constant does not move its argmin. The step size is not untouched. Every step at a fixed learning rate is twice the size the textbook derivation predicts. Here is the rule. Read a constant in front of a loss as a statement about the step size, never as a statement about the solution. Lecture 9 shows where the half genuinely comes from, as the Gaussian negative log likelihood at unit variance. The third hiding place is the worst. The constant is not a default. You can read off anywhere. It has been folded into how a quantity is stored, and the formula that would have displayed it no longer exists. 3 examples. First, the base of the logarithm. Entropies differ by a factor of log 2 between bits and nats, and every library uses the natural logarithm, which has the clean derivative. A paper reporting bits and a run reporting nats disagree by a constant that appears in neither. Lecture 1 fixed nats for this course. Second, variance against standard deviation. The same letter sigma names both, and identifiers, such as running variance and log variance, hold neither. Third, a scale folded into initialization. The factor square root of 2 over n, which keeps activations from collapsing with depth, is not in the forward pass at all. It was applied once to the initial weights, and after that it is invisible. Lecture 19 derives it. This is my favorite frame in the lecture. Let us take it slowly. The attention scale is exposed nowhere, so we recover it from behavior alone. Give the mechanism exactly 2 keys. Write the 2 logits as the query dotted with each key and call the unknown scale s. Then the ratio of the 2 softmax weights is e to the power s times the gap between the logits. So s is the logarithm of that ratio divided by the gap. Take the value matrix to be the 2 by 2 identity, and the return value is the weight vector itself. 7 lines of code and no privileged information. Sweep d sub k over 4, 1664, 256, and 1024. The scales come back as 1/2, 1/4, 1/8, 1/16, and 1/32. Those are exactly 1 over the square root of d sub k. The worst disagreement across the sweep is about 4 in 10 to the 16th, machine rounding error. Nobody told the script what the constant was. It read it off. Lecture 22 asks whether that constant is the right one. Finally, the thing itself. One equation from one paper, and the code that computes it, read line by line. Now the paper itself. Attention of q, k, and v equals softmax of qk transpose over the square root of d sub k, all applied to v. Let us name every symbol. Q holds the queries, 1 row per position being answered. K holds the keys, 1 row per position read. V holds the values, the content actually averaged. And d sub k is the dimension of the keys, which sets the scale and nothing else. For shapes, q is nq by d sub k, and k is nk by d sub k. V is nk by d sub v, and out is nq by d sub v. Now, 4 things the paper leaves to the reader. The softmax does not say which axis it acts on, and the equation is wrong if you pick the other one. The batch and head axes are absent. Masking is absent, and q, k, and v are themselves learned linear images of the same input, which the formula never shows. Restore the two suppressed axes, batch B and head H, and the equation becomes two contractions. The first line, scores equals the in and sum of the string bhqd, comma bhkd, arrow bhqk applied to q and k. Then divide by the square root of d sub k. The second line, out equals in sum of the string bhqk, comma bhkd, arrow bhqd. Its inputs are the softmax of the scores along the last axis, and v. Now read the first string as mathematics. The letter D appears in both inputs and in neither output, so D is the summed index, and D is the paper's D sub K. The letter K appears in the output of the first line and is gone from the second. So the softmax axis and the contracted axis are the same axis. That is the entire content of the sentence the paper did not write. Those two lines are a literal transcription. Every index came from the equation, and no step was taken that the paper does not license. The library does not compute it that way. Scaled dot product attention is one fused kernel. It never materializes the score matrix, chooses its own summation order, and may dispatch to different code on different hardware. So, if our transcription is right, the two should agree to rounding error, and not better. They do. The maximum absolute difference is about 6 in 10 to the 16th. As an independent second check, the rows of our attention matrix sum to 1, with worst error about 4 in 10 to the 16th. That says the softmax ran along the axis we claimed. Lecture 23 is about why that fused kernel exists. Here is the standard. A literal transcription of the paper reproduces the production kernel to machine precision. Not that the code looks like the formula, but that a run says they are the same function. Three things sit in every implementation and nowhere in equation 1. None of the three is optional, and none of them is a detail. First, the causal mask. Setting the scores above the diagonal to minus infinity before the softmax is what makes the model a language model at all. It changes the output by about 3.2, which is not a rounding effect. The paper puts it in prose in the next subsection. Second, the shift by the maximum. Every implementation computes the softmax of z as the softmax of z minus the largest entry of z. That is exact by shift invariance. No paper writes it. Without it, on low jits near 1,000, the naive form returns not a number 3 times over. The library returns about 9/100, about a quarter, and about 2/3. Lecture 10 derives why the shift is safe. Third, the reshape into heads. The paper's single model dimension is split into heads and moved to its own axis. That is bookkeeping and not mathematics until Lecture 20 makes it a direct sum. Here is the transferable part, and it is 6 steps rather than a talent. 1. Find the equation and write down every shape it implies before you open the repository. If you cannot say what shape each symbol has, you have not finished reading the paper. 2. Find the call site, not the definition. The call shows which defaults were accepted in silence. 3. Check the reduction, mean or sum, and over which axis. That is the factor of the batch size. 4. Check where the constants live. Argument, literal, or absorbed, and the third is the one people miss. 5. Make the library tell you a constant you were not given, exactly as we did for 1 over the square root of d sub k 6. Only then believe you have read it, because an untested transcription is a conjecture. Steps 5 and 6 are the ones nobody does, and they are the ones that turn reading into knowledge. The library is an oracle you may interrogate. 5 things worth keeping from Lecture 3. First, symbols became identifiers, and the map is neither 1-to-1 nor onto. Epsilon is epsilon in 2 places with 2 meanings, and the flat theta is never formed. Second, a summed index is a contracted axis, and the leading axis is the sample index no paper writes. Loop against batch agreed to about 7 in 10 to the 15th. Third, the expectation became a reduction with a default. Mean against sum scales the loss and every gradient by the batch size, 64 here, and the learning rate with it. Fourth, constants hide as a default argument, a hard-coded literal, or a parameterization. The textbook 1/2 is in none of them, and its absence doubles every step at a ratio of exactly 2. Fifth, and best, a constant exposed nowhere can still be measured. We read the attention scale of behavior to about 4 in 10 to the 16th. Our transcription of equation 1 matched the fused kernel to about 6 in 10 to the 16th. Next time, automatic differentiation. Read section 5.6 of Daisenroth-Feisal and Ong, prints on gradients and initialization, and Bishop's backpropagation chapter. Lecture 4 separates the three things called differentiation, builds the computational graph, derives reverse mode as the adjoint of a linear map, and makes gradient checking a discipline.